Live streams over here. Yeah. Okay, now this is slightly annoying.
You can hide that.
Let's see.
Hide floating meeting controls.
Okay. Oops.
Better?
Yeah. So now I can't. Okay. Cool. I think we're good. Anka, do you see me? Are you? I should be. No.
Yes, if you want that on, we have to switch that camera. So you go to video. Oh, yeah, don't have to start video yet. Click on start video and then pick the right camera. Yeah, pick the other camera. Pick the
USB.
It's us. Oh, and switch the except they're sort of backwards. I think. So you go to the video settings and turn off Mirror My Video. Video settings. Mirror My Video. Turn that off. Good. Excellent.
Okay.
How's that look?
Okay, and remind me, I hid this somewhere here. Oh, this is like
so
cool.
Press escape to see those back.
Yeah, got that.
Okay.
Awesome.
We're here for you.
We're good. Thank you. That was super helpful. That would have taken me like a month to figure out.
I love being asked for by you.
Anka, are we good? Awesome, awesome. Hopefully people remote can hear me. Glad to see live audience here. I've lost track of what lecture week we're on, but I know we're getting like toward the end of the world. And we'll talk mostly about transformers today. And so in particular, I want to do sort of three things. I want to review the key concepts behind transformers, the query key value, which I find really obvious after I know what it means and really confusing the first 3 times I saw it. So I want to make sure you get that. I thought we'd play a little bit with codecs. Anybody use codecs? Okay, we'll ask you later how it goes. This is OpenAI, Microsoft's effort to put you guys all out of, to help make your life be much easier, help you with coding. So a current application of transformers. And then I want to talk a lot about projects and sort of how to make cool projects, because Conrad and I are getting lots of questions. Any bureaucracy, Anka? Are we good?
We are good.
We are good. Okay. Like to hear we're good. Okay. So what's the process of natural language understanding? To use a general word, take the string of characters, English characters, Chinese characters, whatever, break them up into tokens. We'll talk about that in a second. Map each token to a vector, like a 768-dimensional vector. Compute self-attention, which is the magic part we'll talk about. And then use this in a transformer-based encoder-decoder model. We saw these before, that you take in some sentence, je suis étudiant, feed it into an encoder. The encoder then takes it, makes some vector, feeds it to a decoder. The decoder then generates a sequence, I am a student. Instead of plugging a recurrent neural net into the encoder or decoder, we're going to plug in a transformer. So it takes the whole sentence in one big piece. Question?
I just asked sort of a question in the last lecture related to this.
Yeah.
So in the worksheet, we were and lecture 12, we were showing like that matrix was like a heat map.
So I have a heat map that maps je suis étudiant, each word there, to I am a student. And there's a roughly, slightly, but not quite one-to-one mapping. Yeah.
So how does that account for when it's not one-to-one? So we're sort of like multiple boxes shaded. How does the neural net
So how does a neural net understand that there is not a one-to-one mapping? So in an encoder, we're going to encode a sequence of tokens. We'll get there in a second. But for the moment, imagine a token to be a word. It's not quite right, but imagine a token to be a word. We've got 3 words. Je suis étudiant. They get mapped in. We now have a vector encoding where we're going to have each of those words, each of those tokens encoded as a vector. We will send those vectors over to the decoder. The decoder is then going to walk through and look at each of those, starting with je, which will turn out to map to I. It'll produce the I. It'll look at I and those 3 things and see what comes next. And what's going to come next is going to be, it'll pay attention to suis, which maps to am. Then it's going to look to say what comes next given the context I am, and say what word comes next. And it will look at étudiant, which means student, but it will then map that and generate the English, which you need a, right? You don't say I am a student in grammatical English. And in fact, in a recurrent neural net, it'll generate them sequentially. In a transformer, it's going to do the whole thing in parallel. But note that what it's doing in each case is paying attention to, which is the core of today, giving weight to each sequential word in the input, the encoder, and in the decoder, it's paying attention both to the other words that have already been output and to the encodings. Does that make sense? So to do a good job of translation, you want to both pay attention to the translation and to the input.
So it's a product of like the literal translation, also making sense of the words that came before.
The literal translation, the generation of the word a in a modern transformer is a function of all of the words on the input, je suis étudiant, and all of the words on the output. I am student, all affect it, because if it's we are students, it will be we are some students or some different word, right? We have to have singular plural accordance in English. Make sense? Yeah.
We have a question from Sandana. The question is, so first layer gives more word embeddings that are not context sensitive. So if we only needed the translation of each word, a shallow input would be fine. But if we wanted a sentence-aware translation, we would have input filters.
So I won't repeat the question because the answer is going to be clear. We're going to map each token to a static vector encoding. There'll be a vector for je, a vector for suis, a vector for étudiant. So we'll have those vectors which are fixed. You could then translate those back again, which would work great for languages which are unambiguous, which have a single meaning for every word. The languages most of us speak, that would be, say, particularly English and Chinese, are extremely ambiguous. And each word means different things. You think I means something, but unfortunately that's often used for the Roman numeral indicating the first item of a set of chapters or something, right? So an am could be a misspelled AM morning thing. Every word's ambiguous. So if you had no ambiguity in language, you would map an English word to a vector, map that vector to a French word or a Chinese word, and you'd be done. And I'd be out of a job. But it's not the case, right? It really is the case that the meaning of a word, the right word to use, depends on the context. And in particular, note that the word a in English depends upon a non-existing context. Suis étudiant, am student, is the a in between. It doesn't even exist in French. Yes? We'll get to what a token is in a second. That's on the next slide. Correct. On the encoder, we're using attention only on the input. The encoder only gets the input sentence and does self-attention. It gives attention in the standard version to every token in the input. The decoder uses attention both on the encoding of the input and on the output.
Does it work on the attention of the output that has been given, or the language corpus of the language that you want to translate?
The attention on the output, we're not going to know. And at runtime, at training time, we'll have an input and an output. Often we'll use the same input and the same output. We'll just mask half the words, 15% of them to be precise. We'll remove 15% of the words. We'll predict those 15%. So often we'll self-train by removing 15% of the words. In that case, we have an input and an output. And we will then give attention during training to all the other words that are known in the output. And in some sense, to think of it as giving attention to the other things being predicted. So the word I would like to generate for A is a function of the word I would like to generate for am and for student. Right? Note that at runtime, I only know if I'm generating sequentially, I know the words I've generated so far and not the future ones. Make sense? So if I'm generating things words sequentially, word after word, if I have I am, I can now pay attention to I and am. But note that A doesn't depend upon I am. It depends upon the future. Right? Because I am happy does not have an A in it. Well, maybe it does. Crap. I am a happy student. So I got to look 2 words in the future. I am a happy student, or I am happy, period. Those have different things there. So note that the attention needs to go also on the things you're predicting to have in the future. Does that make sense? So we're running these things as a transformer, much more as a block, where we have both the actual words we've generated and the words, the encodings of the words, the embeddings that we're thinking of generating. During training, we're using masking and attention. Sorry, I'm repeating. People can't hear you remotely. Yeah, keep going.
Yeah. So training is masking and attention, and during the prediction time, we're using whatever context-based encoding of the input plus whatever we have as the output, right?
Right. During training, there's masking, and during testing, there's no masking, and you're going to generate future words based on what you've seen so far. Cool. Okay, so tokenization. The problem with languages is there are lots of words. When I worked at Google a decade ago, we encoded every word in English to a vector, 1 by 1, and used about a vocabulary of 1 million words. Now, 1 million is an insanely large vocabulary. Most native speakers of English have a vocabulary of maybe 40 or 50,000 words. A good Penn student, native speaker, might have a vocabulary of 100,000. But 1 million is not unreasonable because it includes names, it includes misspellings. When I was there, we looked at Britney Spears, and there were dozens and dozens of ways of spelling her names that were used every day in the search engine. So there's a problem. Yes?
Follow-up question in chat. So there would be some form of leakage since decoders already know the target words that they need to predict. I'm not sure I understand the target self-attention decoders.
Yeah, I'm going to punt on that for now and come back later. So the problem is there are too many words, and including misspellings and names and everything that happens. And you'd like to have a model that does every word without having too many of them. It starts to get big. If you're mapping each of 1 million words to a 300-dimensional vector, that's 300 million numbers. That's okay. But if you're doing it it gets bigger. So what people do is some version of breaking up words into pieces. And there are a bunch of variations that are all basically the same. The most commonly used ones are called word piece or byte pair encoding. Oops, somehow there's an extra A on Roberta. And the idea is that you break up the word into substrings that are frequently reoccurring. So if you take the word transformers, you might see frequently in English the word transform, and frequently the string transform, and frequently the string ERS, which is a common ending in English, as is ER, but ERS is common enough that you might find this broken up into 2 pieces. And then what they will do is break things, is do some sort of a search over all of the short substrings to find, for example, substrings that show up a lot, and then give a frequent substring its own token, its own encoding, and rare substrings would then be composed by definition of smaller ones, right? You start with 26 letters in English. Okay, not quite. You have numbers and punctuation. You can start with a few hundred characters, right, in English, and then group them together. So the simplest thing is a byte pair encoding, which just counts them. What are the most frequent substrings? And then just take enough of them until you have whatever much you can fit in memory, or you want as a standard piece, right? So you have frequent substrings, SUB, STRING, ERS, right? Frequent might be a string thing. And then Ly, LY. So frequently might be frequent plus Ly. That makes sense for a byte pair encoding. You can show each string as a byte. Or instead of that, you can be sort of fancier and use a word piece encoding, same idea, but instead you're trying to maximize the likelihood of the training data. You're trying to not just count them, but to use ones that in some sense are more predictive. The details really don't matter, except that they differ from system to system. There are a bunch of different ones, mostly called byte pair encoding or word piece this year. And if you look at something like a Titan RX has 24 GB of VRAM, what you'll see under the hood is some representation that looks like, and here's BERT, A, Titan, R, and then T with a special hash before it, showing the T's in the middle of a sentence of a word. It's not a word initial T, it's a middle one. And then a X, showing that the X is inside a word. It's not a word initial X. And then has, and then 24, and then GB, which remember 24 GB. This GB, unlike a separate GB, is inside a word. Why is that important? Is GB with a space before it different from a GB with no space before it? Yes, with a space one could mean Great Britain. Excellent, full credit, right? So 24 GB clearly means gigabytes. 24 space GB, we're going to know actually means gigabytes, but something space GB often means Great Britain. So they make a difference. And you can see things broken up. Other ones, I didn't run the same one on it, but here's GPT-3, which has the text you can't see. The animal didn't. So GPT-3 tokenizes, and everything is different, with a didn't, D-I-D-N is one token, and apostrophe T is a second token. Other things like BERT, I think, do didn't, and then apostrophe separately, and then a T separately. Right, so they're different. You got to be consistent within it. Cross the street because it was too tired. Okay, and those are all single words, I guess. Period. Yes?
Do the models themselves learn how to this? Like, how do you like didn't versus apostrophe or apostrophe separately?
When you use a given piece of software, a given model like BERT or Roberta or GPT-3, they all come with a built-in tokenizer.
Okay, so the built-in is decided by the human, not
the built-in is decided by the human. The designer made a choice. Remember that you can't train Roberta at home. You can fine-tune it. We'll get there, but you can't train it because you don't have enough text and enough compute power. So you're going to use some pre-trained model, and some engineer at some company like OpenAI, Microsoft, or like Google has decided which tokenizer they want to use, and you're going to use their tokenizer. And all you're going to remember is that if you switch from GPT-3 to Roberta, you're using a different tokenizer. And the other thing you're going to remember is that some things the embeddings are for a word, like transform or frequent, and they make sense. And sometimes the embeddings are for a token like GB. And now you got to be worried a little bit about hash GB. Does it cleanly mean gigabyte? Or does there other things that have a GB in it? So sometimes the embeddings are a little weird because these short ERS could have multiple meanings. Does that make sense? In the back, yeah.
Review how we handle these like ambiguous pronouns here. Like it was too tired, clearly the animal, but if it said didn't cross the street because it was too long.
So how do we handle the ambiguity of a word it? Note that at the moment, all we've done is tokenized a string of characters, and it is a token. And that token will have a single embedding, which does not account for the ambiguity. It's a token to embedding mapping, say 768 for the ones up here. Now, how does the world handle the fact that it refers to different things? We're going to need to build a transformer. We haven't gotten there yet. We'll get there. This good for tokens? And some tokens, things have hash before them to show that it's in the middle of things. Other tokenizers have a underscore or something after them. So here is a BERT encoding. We've taken a tokenization of the, animal, did, apostrophe T, separate tokens. BERT breaks these up this way, cross the street because it was tire, and then off the screen is a separate D. And then after that's a period. So BERT breaks up tired into tire plus D. Ooh, we worry about the word tire in English. If we're in Britain, it might have a Y in it or something, but tire could be on a car, but the context is going to help us. So makes sense. So we've got this tokenized sentence. Now, what BERT is going to do is to pay self-attention. Every word in this sentence will have some weight of how much it should be combined with every other word of the sentence, which will allow us to have the it have different meanings. Because how do we know that the it was the animal and not the street? The animal didn't cross the street because it had a grate over it, was painted pink, was scared. Oh, they're all weird and different. We think animals are more likely to be scared than streets, and maybe animals are less likely to have grates on them than streets are. Make sense? We need to know the context. So when we find the context-sensitive embedding of it, what we're going to do is measure in some sense, and we'll lose a bunch of times, how similar is it to each of these words here. That will give us a weight, an attention weight, and then we will have an embedding for this it, which is a weighted sum of all the embeddings of the words in the same sentence. Okay, maybe this is clear. Let's do it in detail, step by step. So in particular, we're going to take every word it, call that the query. We're going to measure how similar, and there are about 3 different ways to do it, but the simplest one is a dot product. How similar its embedding is to that of each of the words in the document. That's the key. So you have a query key similarity. That will give us in the end a matrix, which is vocabulary by vocabulary, right? Self-attention is n squared. Similarity of every word to every word. But it's the same sentence, right? This is almost like a kernel. Similarity, similarity. We take the query times the key. Then to make the math work out nicely scaling, we divide by the square root of how long the vector is, which is not important, but it keeps the numbers reasonable, sort of normalizes it. That's now our weight. We have a weight between this embedding and each word's embedding. Then we take the value, which confusingly is exactly the same as the key. And we say, what's the weight of each of the values? So what do I mean? We take how similar is it to cross? That's query times key, dot product, inner product. Then multiply that by the embedding for cross. We then take how similar is it to the. That gives us similarity. We add on that weight times the embedding for the. We take how similar is it to street, another dot product. How similar that is, we weight that by the vector for street, the v's, and we add them all up. That then gives us a context-sensitive embedding for it that tells us, it is similar to some degree to each of these other embeddings, and we just sum them all up in a weighted average. And that gives us a context-sensitive embedding. That's the hardest part of the whole NLP section. So questions? Yeah. The key and the value, first of all, are both identically the same. The key, if you take the word cross, it has a vector embedding. But that vector embedding is used in 2 different ways. One is decide how similar is cross to it. So we take the dot product of cross and it embeddings, and that measures a similarity of cross to it, right? Two things that are highly similar have a big dot product, they're orthogonal, they're zero. So the first use of the cross embedding is as a key. And this comes out from the database lookup, a key and a value. Think of a Python dictionary. So the first thing is we're doing a soft lookup. We're saying how similar is cross to it. That key gives us a weight. Make sense? Now we're going to take that weight and multiply it by the actual 768 dimensional embedding of cross. That's the value for cross. Oh, which is exactly the same as the key for cross. So the attention score is Q dot K, is the query dotted into the key. I'm not sure I heard your question. Did that answer it? Yes, the similarity of the query to the key is the attention score, right? And to be super precise about it, in fact, we take the query times the key, that gives us a similarity. Then we push it through a softmax to make it go something that looks like a 0, 1 number. So to be more precise, the dot product similarity is the softmax of the dot product. Right, so we throw in this little nonlinearity to make that dot product map into something that really looks like a weight, right? A set of numbers between 0 and 1 that will sum up nicely. Yes? Well, the query here, is there a question in this world? What's the query? Each word in the sentence is the query. So we're no longer doing a query in the sense of a question answering query. This is a highly technical jargon for self-attention, but nonetheless, it's the core of all transformers. And the idea that says that you take every word in the sentence as a query, and you compare it to every word in the sentence as a key. If you've got n words, you'll have n by n. Every one of the n words has got some similarity to each of the other n words. And then to find the embedding, again, for any word it, I will take the attention weight for each of the words in the window, multiplied by the embedding of those words, and sum them up. So it's a weighted average of the embeddings of all the words. I keep saying sentence, but really it's a window. You specify how many tokens long the window is. Yeah. The value is the context oblivious embedding of each word. Go ahead. Wouldn't it be nice to use the context sensitive embedding? Yeah, that's sort of cool. And so on the other hand, we want things to run fast and in parallel. So what are we going to do? I've showed you the raw input layer, which has words and embeddings. And now we're going to actually do this a bunch of times in parallel. The same way for any neural net, we have a whole bunch of hidden layers. So we'll do this with a bunch of different weights and embeddings, which are called heads. And then we'll do this on a bunch of layers. So you might have 12 heads and 12 layers, and sort of a standard architecture. So once I've embedded the words in the first layer was just the context oblivious embeddings. Now I take the outputs, which are these context sensitive ones, and I repeat the whole process, giving self-attention between all of the context sensitive embeddings to get more sensitive ones. I do this, say, 12 times. So I'm going to get what you want, but I'm going to get it precisely by having multiple layers in the network. Good question. Yes?
Papa asked, do we consider the order of sequence of words too? I mean, how two words are positioning similar?
Ah, that's a great question. Do we consider the order of the sequence? Where has order shown up so far in this slide? Nowhere. Do we think that does order matter in most human languages? Yeah, I think there's one, Walpuri, where it allegedly does not matter. And there are about 10,000 others that are documented where it does matter, right? So in general, for any language that you're likely to speak, I'll bet none of you speak Walpuri, order matters. So we do one more trick. We take the tokens and just give them a number, 1, 2, 3, 4, 5, 6, 7, their order. And we then map that into some embedding space, the save 768 embedding space. So we encode the order of the words. And that's added in, and that's then part of the model. And I'm going to skip over most of the details of that, except to note that, yes, it's critical that you encode not just the word, but something that captures where the word is in the sequence. Because it really does matter what order things come in. Right? Super good. So again, we've done this once, but now we can run the exact same algorithm that takes the input for the first layer and says, okay, let's start with a different initial random seed and learn something. And in the first case I gave you, it was showing attention to, where was it? Let's see, to cross the street. Didn't cross the street. Now the it may be paying attention positively or negatively to was too tired. Whoa. Okay, that's still up there. Good. There's problems on the screen there. It's not your problem. Cool. So what happens is we'll have a whole bunch of heads. Think of a head as being something that is equivalent to having different hidden units. The same way in a CNN, you're going to have for a given, not quite the same, for a given window, it maps to different places in the hidden layer. What I'm going to have here is not just one context sensitive embedding for it, but say 12 of them. Does that make sense? With different weights on them, different attention. So it's not that the BERT will pay attention only to one given sequence of intentions. It's going to pay attention 12 different ways, 12 different sets of embeddings with different weights. Yeah. How can one word have different weights? So what's going to happen is as we do our learning, we're going to have to shift the embeddings, right? So yes, so what's the embedding? The embedding is this, the attention is the similarity between the query, the word it, and the key, the word animal or whatever. With me? So we started with some fixed embedding as a starting point, but we're going to have to learn a whole bunch of different internal embeddings. How are we going to do that? So I
The similarity between the embedding of one query with same. So how are we modifying that to get different attention?
So each different attention head is effectively going to learn different embeddings for each of the words. Right? The attention is only a function, always the same attention. Query dotted into key, that's the attention, softmax. So the attention really is the same, but I think the way to think of it is that each word can now have 12 different embeddings for that same word. If you think about it, maybe more, maybe less obvious, as you go deeper and deeper in layers, you're having different, each layer makes a new different context sensitive embedding for the word, right? So as you go from layer 1 to layer 12, you're getting an embedding that's context sensitive and more context sensitive and more context sensitive. And sort of like a CNN, as you go deeper, when you start initially, it'll tend to have things that are more local connections. As you go deeper, it'll tend to have more global, farther away connections. So I think that piece is maybe obvious that as you go deeper in the network, you're going to get a context sensitive embedding that's more and more context sensitive. What's maybe less obvious is these are non-linear models. They're neural nets. They're started by a random initialization and solved by gradient descent. So depending upon what random initialization you give, you will then get different embeddings, context-sensitive embeddings. And rather than just picking one context-sensitive embedding, we're going to pick 12 different ones.
Is each layer one head?
Now, if each layer had one head, then you would have then you wouldn't have what I'm showing here. In that case, the word it would always have the same, well, different layers would pay attention to different things, right? But what we're doing is not just paying different attention to different things as we go deeper, but in parallel across each layer, we're learning a different embedding of it and a different embedding of the and of animal and didn't. And therefore, within one layer, we're finding different embeddings of it, which therefore by definition pay different attention to different words. So if you think about it, each word like it has lots of meanings, lots of possible things, because it could be the animal, it could be the street. There are different things it could mean. They could be tired, could be the meaning of it in some sense. And so each of these different heads is learning a different embedding of it in parallel across one layer. And each of these different meanings will then have different similarities to other words. So we're getting something which is allowing us to capture parallelism of the ambiguity of English. Yeah. Yeah, so the heads are like different filters in a given layer, right? So we're going to have typically of order a dozen filters, heads which allow different embeddings, which allow different attentions to be paid, which in some sense capture different meanings. Meanings are of a sloppy term here. And then we're going to go deep as well, having a dozen each of them. Make sense? It's a weird structure, but it works very well because it allows us to simultaneously capture the ambiguity of language in the given context and make it more and more context sensitive. Then the whole thing is just solved with gradient descent. Cool. You'll get a chance to play with these in pods and do things. So if you look at the whole picture, this is from the original BERT paper, the whole thing looks hopelessly messy. But what do you get? You got some inputs, words that are tokenized. Each token then gets mapped to an embedding, a context oblivious embedding. That's the input embedding. Then you add in the positional encoding that says for each token, what is it first, second, third, fourth, fifth in the sequence? So then and that's just added in, another 768 dimensional vector. Now that goes into something that's going to be repeated n times, like a dozen times. And within each head, there'll be a multi-head attention, maybe a dozen different filters, each of them doing a different context-specific embedding with different, therefore, attentions. We're going to add those together and normalize them, run them through a little feed-forward network, run them, and then feed them through a dozen layers. Now what we have is something that has taken this original input sequence and generated a a dozen different context sensitive embeddings of each of the tokens in each of the layers, but let's take the output one. Now we can send that over to something which is going to actually predict the outputs. And the outputs could either be, in some cases, the same sentence shifted by one, predict one word in the future, or in a more modern version, something that takes 10% of the words missed and tries to reconstruct them. So in the original input, you've got 15%, I said 10%, 15% of the words masked, and then you predict those. So you have the ones you're trying to predict, right? 15% removed, the 15% you're trying to predict. Take those, embed them, add in the same positional encoding, first, second, third, fourth, fifth, you know which one they are, run that through the same style, but with different weights of encoding, right? Multiple heads, same number of heads, and then take in, so that's paying attention to itself, the output only. Now take in the encoding from the inputs right? The 12 heads of the output there, feed those in, combine them together with the encoding the output, run that through a whole bunch of times. This happens again, say a dozen times, and then run the thing through a softmax and get a probability over each of the outputs. So it's really messy, but all the pieces are the same, basically. All of them have repeated query key value embeddings. And at the end of the day, you have something that, given an input, generates a model that predicts what are likely to be either missing words or words afterwards, following words. Cool. Yes? How does the masking fit in during training? So the input is a sequence of words. I went to school yesterday and had a great time. We break those into tokens. And then we take 15% in the current implementations of those tokens, randomly 15%, and delete them, mask them. In fact, can we generate more data than just that one thing with no more data? I've got a sentence. I've used it once. Can I use the same sentence again? Mask it again. It's got a fancy word like dynamic masking. So in the old days, like 3 years ago, they would take one sentence, mask it once, and throw it away. In the modern day, we want more data. We want data augmentation. Take the same sentence or long sequence of words and mask it 100 times with a different random 15% each time and predict the ones that are missing. Awesome, 100 times as much data with no more text. Because I only have 500 million words of text, so I need to reuse it. Make sense? Yeah.
When you mask the input, what's the output of that?
When you mask the input, the output usually is to predict the words that were masked.
The input to, I mean, what is the outputs in the diagram? Is it just the masked word or is it the whole sentence again?
Usually you just predict the masked word. You could also predict the whole sentence, right? So in some sense, maybe it doesn't matter. Right? And again, I'm trying to summarize dozens of different algorithms. So there's lots of variations on this theme. And exactly how it works is different for BERT versus Roberta versus GPT-3. But they're all using something of that form. Right? So the thing you should understand, one second, is that there are 3 or 4 different kinds of word piece or byte pair encodings that are used. There's a bunch of different representations in the inside. When they say BERT, nobody means BERT. There's a dozen BERT. Some of them are bigger, some are smaller. There's big BERT and little BERT and small BERT and cousin to BERT. And there are variations like the still BERT. And so there's lots and lots and lots. You go to Hugging Face, you'll see that there's 40 different BERT-like models, all of which will have subtly different training and different structures, and all of which are slightly better for different problems. There's similarity BERT to measure sentence similarities. Some of them actually, in addition to masking, try and predict the whole sentence before or the whole sentence afterwards. That's out of fashion this year. Last year it seemed to help. So they're all subtly different. That's a long non-answer, except to say not to get too attached to any one particular detail, but to note that they're all self-supervised, right? There's no matched English sentence, Chinese sentence like the old days. This is all a single sentence predicting either the next word or the masked words or the next sentence. Lots of variations. Often there's a separate special token, which is start of sentence token, a CLS token or something, which can also be learned to summarize the content of the whole sentence. Those are different again between BERT and Roberta, even though the basic architecture all looks the same. So take cis522, they'll spend more time talking about all these details. But for this course, you should have the big idea and not get too concerned as to which exact tokenization or method is used. Cool. So the 2 big things that are used are BERT and the BERT family. And by the way, when I say BERT, My students, I say to use BERT. What I really mean is use Roberta, which is a more modern BERT, has the exact same size, but has different training, a lot more data behind it. So it's better, basically. Transformer, masked word. The big change in the last few years, well, there are two big differences between BERT and GPT-3. The training size. One is in the millions, hundreds of millions, one's in the hundreds of billions of tokens or words, parameters. The training set's actually bigger. These are all, remember the double descent? These are all trained with, often trained with at least as many parameters as they have words. And BERT is nice because it's open source. You can grab it. GPT-2, you can get the code for. GPT-3 is locked away safely on a company that's called OpenAI, but basically Microsoft put in $1 billion and owns the exclusive rights. So it's easy to play with, but impossible to get a hold of the actual source code. Which means that for some experiments, you can only do experiments that they permit, right? They give you an API. If they want to let you fine tune it, you can fine tune it. If they don't want you to let you fine tune it, you can't. Does that make sense on the GPT-3, needless to say, is better than BERT in the sense of out of the box because it's much bigger. Cool, fine tuning. The other piece here, which the most current uses of these start with some pre-trained model, BERT, by which I mean Roberta or DistillBERT, or GPT-3. And then they say, take this pre-trained model given to you by Google or OpenAI, and then fine tune it. And there's a bunch of different ways to fine tune a model. Fine tuning just means start with that initialization, do some gradient descent. You could fine tune the whole model, adjust all the parameters, or you could say, I'm only going to adjust the output layer, or I'm only going to adjust the last 4 layers, which is often the best thing to do. So there's a lot of choices there. And the fine tuning can either be unsupervised or supervised. How would I do a unsupervised fine tuning of BERT? What would that look like? And why would I want to do it? Yeah.
Maybe if like your vocabulary develops over time.
If my vocabulary develops over time, sure. What's more common? What is BERT trained on, roughly speaking? What's it likely you would train a model on if you're trying to train on? The web, Wikipedia, books out of print, whatever you can find, right? It's trained on a convenience sample of the words that are readily available, which are the things you can scrape off the web mostly, right? That's great, but what if I want to use this on some specialized piece, like say, physician's notes in the hospital? So maybe I want to do a medical BERT that will be trained to be specialized for the physician's notes with lots of RX 1PD per diem, or whatever jargon doctors make with whatever misspellings they make. Make sense? And maybe words have different meanings in the doctor world than they do on the open web, right? Doctors mostly don't swear in their notes. It's got different meanings in them, right? So I might take a bunch of notes, people have done this at Penn, from the hospital, take all of the medical records of all the notes, and then fine-tune Penn on it, fine-tune BERT on it. Now, how would I, so it'll capture the meanings that are more typical. How would I fine-tune it though? Got no labels. Mask it, right? Start with the initial pre-trained BERT and then just do the standard BERT training with the mask on my small data set, right? Maybe 100 million words I could get of medical records. Make sense? So I can tune the weights on BERT so they're more indicative of the co-occurrence patterns that show up in medical records versus on the web. By the way, people tried that. It doesn't help very much. Yeah. Good. So that's unsupervised. Could I do a supervised training? I want to train Bert to recognize, okay, hate speech. Just talking to a student who's working in Myanmar. Oh, that's the first problem. He's not going to work in English mostly, but okay. Working with companies like Facebook where they'd like to recognize threatening hate speech, sort of a deal in Myanmar these days. And you'd like to train a model that takes BERT and predicts for a given post, hate speech, not hate speech. First of all, you train a bunch of native speakers to label it, right? You get a BERT trained in that language, unsupervised. Now what you can do is take your unsupervised model and either take the output of it and put it into maybe just a logistic regression. Hate speech, yes, not hate speech, no. Or you could propagate the changes back further and let the last 4 layers of BERT adjust themselves. Make sense? And GPT-3 is now allowing similar sorts of tuning. Cool. Okay, last piece before we go to talk about projects. GPT-3 is sort of a modern transformer, widely used. Lots of companies are using it. How many people have played with GPT-3? Oh, few, cool. So it's done for all sorts of things where you have some sequence of words and predict which words are following. And I think rather than playing the riddle game, I thought it'd be fun to go look at, come on, give me back my computer. GPT-3 no. Is sort of a modern transformer. That's weird. Widely used, lots of companies are using it. How many people have played with GPT-3? Why is my thing talking at me? So it's done for all sorts of things. Sorry, my computer somehow repeating me back with some lags. I thought it'd be fun to go over to OpenAI and to play with Codex. Anybody play with Codex or GitHub Copilot? Nobody? Yeah, one. Okay, cool. So basically, you can take the GPT-3 model and then fine tune it on software, code, Python preferably, but JavaScript, whatever you want. I like Python. First of all, where do you get a whole bunch of Python code? What? Kaggle's a little bit. Yeah, I get some in Kaggle. Think bigger. This is not just data science. This is all of coding. GitHub. You grab all the publicly available stuff on GitHub as a starting point, and a few other ones. But that would be the sort of ones you'd start. And now what you can do is fine tune the model. The model's trained on English, but now it's fine tuned on, well, what does code look like? It's a mixture of English and, say, Python. And you can now train it, and it will do auto completion. And there's a sort of cool chart. So let's just go sort of, you can open a screen there. Okay, so people can almost see that? Make it bigger. So you can type in, here's their code example. You type in this thing, quote, 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 ask the user for their name to say hello, and you type submit it, it sends it to GPT-3 Codex, and it generates the auto completion. Okay, that one's sort of easy, and these things tend to memorize a lot. They had to put in automatic safety things to block out all the private keys that are available in the public GitHub. All sorts of things that shouldn't have been there. But it's sort of fun. Let's see, let's generate, oh, I don't want caps. Generate a list of names. People's names, I mean. People, doesn't matter if I misspell names. Okay, let's try that one. So, okay, it's going out of control here. But let's sort of start to look at the top of the code there. So it says def generate num names. It gives comments there. It takes the number of names to generate input, returns a list of names. Let's see, names is equal to a list for I in the range, names that append. Hold it. Is this going to work? Okay, it's got to call generate names. There's generate names, generate a single name, return random choice first names plus last name. Okay, that's cool. Where is it getting the first name and the last name? That didn't work. It generates a second one. These things are stochastic. Each time it runs, it will have a different random number. It will generate a different set of code. So what you should start to see is, on the one hand, it's sort of cool. It generates code and comments. And you can use this inside as you're typing along. This is autocomplete on steroids. And there are cool examples on the web where you're about to type the comment so it can autocomplete the code. It autocompletes the comment before you've even done it, because it knows that's what people usually do in that situation. On the other hand, what you see is, in this case, it didn't quite do that, because it's taking a random choice of first names and last names. Maybe a second one will do that. The last time I did it, it actually tried generate a list of names from user inputs. Let's try and make something more intelligible. Well, you didn't specify very cleanly. Oh, no, I'm going to submit. Okay, now it works really well. Here it is. Main, no inputs, names while true, input a name. If name equals null, break. Otherwise, append it, print the names are, and print the names. Oh, it did it. Cool. Got to get the right prompt. There's a whole bunch of stuff, by the way, and cool modern stuff. Can you fine tune the input? Can you find a way to train what input should go in to do a better job? Let me do one more and then I'll take comments. Generate a list of people's names from the US Census website. I happen to know that the US website, US Census, has a list of all the names of everybody. And it has nice sort of pieces there. So let's see what it does. So, oops, okay, we're generating a bunch of code, not too much. So, def get names URL response. It's going to, oh, the last time I tried this bit stochastic, it's going to use beautiful soup. Is that a good idea for a way to scrape a website? Anybody use beautiful soup? Nice code, good choice. So it's going to actually try and grab them and do them. Here's a better version of the code, generate for next time. It actually tells me the URL. How did Codex figure out the URL for grabbing the list of names from the census? Magic, psychic. Yeah? Someone else's code. I'm not the first person in the world to write code that scrapes the US Census for names. It's well known in NLP that that's a good source of names. You can get them by year, you can get them by all sorts of things. It's a great source. It looked it up. Now, I haven't tried this one. This is a weird one. But the last time I ran this, I actually copied the URL and pasted it in, and it actually worked. It was the right URL. So it looked up. It has memorized as part of GPT-3 because it's seen this thing enough times. And then it does get names. What you find is that it's a little flaky. Sometimes it's genius. If you give it more detail, like use beautiful soup, then it does a better job. Sometimes it forgets the import statement, so the code doesn't run. So it's super flaky in the sense of generating great code, but it's getting fairly useful already as a code aid, where most of what I do is coding by Google. You Google, you go to Stack Overflow, you then copy the code and paste it in. Oh, they can use Stack Overflow too. They have memorized large pieces of Stack Overflow, and they use GPT-3 effectively as a neural net lookup that grabs the solution from Stack Overflow and throws it. Each time it does it, it's going to give a slightly different answer. Some are good, some are bad. Google, with their version of this, not the OpenAI, but the Google one, now is performing at the level of a competitive programmer on programming competitions by taking code like this, running it 1 million times on a programming challenge problem, and then running each of the 1 million codes run and checking to see which one seems good. And that half the time is the right answer, the winning answer to the competition. So they're flaky still, but they're starting to be really good versions of autocomplete. Cool. Questions on any of this? I want to switch for the last 20, 25 minutes to talk about the final project. I'll take questions one more time. Any questions, Anka? Are we good? People are good. So it's fun. I mean, play with codecs. They're fun. They're just nice to look at. Yeah.
So I guess on the training GPT with like taking a ton of computation, it seems like so big that even the forward pass might start getting expensive. Like, do people have ideas? I guess we have distillation and things like that. Yeah, like are there ideas like what to do once it gets too big?
So the question is the training, of course, is insanely expensive. The running can be expensive. Do people have ideas? And the answer is yes. On the one hand, the current ones, it will cost you pennies per run. But heck, compared to your time, giving Microsoft a few cents for the GPU power to run the forward pass, do I really care compared to how much time a programmer costs? The second answer is yes. People are working really hard. There's a very active research area. Maybe we'll talk about that later in the course of what's called distillation. People are trying really hard to take these models and make them 10 or 100 or 1,000 times smaller, and mostly with quite good results. So it turns out, and this is an important digression, that most deep learning models are insanely overparameterized. You've got 10 or 100 times more parameters than you need to fit the equations. First question, why do we do that? Why not just run something 100 times smaller? Does it work as well?
That was kind of the golden ticket. Like you need the right initial, like theoretically.
It was the golden ticket thing. If you knew how to find it, it would work. But our current gradient descent doesn't tend to find it on a small network. So there's an open research question, which is there a way to directly search and do a better job of gradient descent on a small network? The answer is we don't know. What we're doing better at is distillation, starting with a large network and then using that as a basis to prune or trim or train a smaller network. The answer is we don't know how to do it, but a lot of companies, think of Microsoft and Google and such, want to do it because their biggest cost, apart from labor, apart from you, their biggest cost is, what are they spending money on? Apart from people. Sorry? Compute power. Well, is the cost buying chips? It's actually energy. The cost of a computer for a AWS is actually more money going to the energy for the chip and for the cooling system around it than there is for actually buying the hardware. So in fact, getting energy efficient systems, getting ones that are smaller and faster is a big financial driver. So big companies are very interested in building small, fast models. So yeah, the answer is they're still so useful that spending 5 cents worth of energy for each OpenAI query, fine, who cares? But yes, they'd be happier to save the 5 cents and pocket an extra penny of it and save you the energy. Cool. Projects. So, no, we don't really need to see that either. Let's see. Pull up the chat just in case I want it. Yeah, sort of fun to see people. Okay, final projects. So the biggest question that I think we're getting, we being Conrad and me and the TAs, is you're doing a final project, and how do you do something that's innovative? It's easy to go in and grab a Kaggle problem and code it up. Okay, it's not easy, it's lots of work, and get something that's an adequate performance. Where does the innovation come in? What's the secret to innovating? Is there an abstract answer to that? Depends, yeah, but what does it depend on? Yeah? Knowing your field well. And it's partly knowing what's already there, so looking to see what's out there. It's also figuring out what it is about this problem that is in some sense unique or different. What is it that you can do by knowing the field? And one of the things that companies tell me is they hire people and people come in, and at first, people are great machine learning data scientists, and they're entirely useless. Why are you useless to most companies, even though you really know how to do deep learning well? Because you don't understand their problems. What data sets they have, what questions they're trying to answer, what the actual real loss function is, as opposed to the loss function you know how to optimize. That to actually be useful, mostly you need to figure out what goes in, what goes out, what's the loss function, what's the scope of the problem. So it's very much about thinking what's unique to that problem. So let's try some of these. For some should be obvious, easy ones. For some sort of object recognition. What sort of questions, how does knowing your problem help you with object recognition? You're doing a standard CNN. Why might it help to know something about the world? What are you trying to label? Trying to label emotion in the picture, trying to label the objects? Sure. How would you go about in general training a CNN? Grab a bunch of images, grab a bunch of labels, train the CNN? I see some yeses. I don't think so. Yep.
I don't know if this is what you're getting at, but like the way that you augment the data might depend on like what you're trying to do.
So augmenting the data might help, right? In the sense, do you actually shift the faces a little bit to left or right? Do you flip the faces upside down? Do you rotate the faces by angles? What transformations you do is certainly relevant. Questions in that sense makes sense. But how do most people? I met this guy who has a whole business identifying not safe for work images. He will go to any workplace and try and help them find out how to do an automatic recognizer that says these images should be seen or not seen. And he wants often for if there's something they don't like. If you're showing movies on airplanes or ads, they don't like to show ads that have have airplane crashes in them, for example. Don't want to show news of the airplane crash while you're flying on the airplane, makes the customer sort of antsy. How would you train an automatic recognition system that learned to recognize airplane crashes? You with me? Put some images of airplane crashes, of not airplane crashes. And you want to do this cost effectively because you're a one-person company. Collect 500,000 examples of airplane crashes, 500,000 of non-airplane crashes, train the CNN. Seems like a bad idea. Yep. You might work with the frequencies. There's some sort of a threshold for that. But from a sheer deep learning standpoint, what are you going to start with? How are you going to set up your network? We're missing some really obvious piece that's going to make this feasible on a time scale that the airlines will pay us for. Yep. I'm going to start with something that's already pre-trained. Yes. I'm not going to train the neural net from scratch. I'm going to grab someone else's pre-trained thing. Now, this case should be obvious. I can either use FaceNet or I can use ObjectNet. Which one's probably a better one to start for recognizing plane crashes? ObjectNet's probably better than FaceNet, right? If I want to recognize is someone smiling or not, ObjectNet or FaceNet? Probably FaceNet, right? So for some things, the clever pieces are obvious. Find out which things to start with. Could I be cleverer? Where might I find labeled data? I could pay people to look at tens of thousands of images and label them as plane crash or not plane crash, but most images don't have plane crashes in them. Yeah?
Look at the movie summaries or transcripts.
Look at our movies and find transcripts there. Here's another question. If I'm recognizing stuff in movies, do I have to use a video or can I use a still? I'd start with doing a still, just taking single images. Does this image have a plane crash in it? But I can look for movies. Are there collections of labeled images out there? ImageNet has things, although ImageNet tends again to have lots of objects like Dalmatians and computers and cell phones, and not a lot of things like plane crashes or people eating Chinese food or whatever. Google search is a great way to do it, right? Write a little script, grabs, searches Google image search for things that say airplane crash. You could grab 100 of them, no problem. Is it possible to train an image recognition system with 100 labeled images? Surprisingly, often you can train with small numbers. I think we talked about training to recognize happy or sad tweets from 100 labeled examples, which seems implausible. But what's the magic? How can I train to recognize any tweet as being happy or sad or in the middle? Pre-trained models. How do I recognize with 100 images? Pre-trained models, right? So now where is the work? The work is finding 100 or 1,000 labeled images, maybe with a scraper on Google search, to think about what to pre-train from. Now, an interesting question you could ask, how small can I go? Do I need 10, 100, 1,000? How small labels? How does my accuracy change with the number of labels? I could say, well, it doesn't matter. Once you have them, you do it. But remember, this guy's labeling lots of things as not safe for lots of different works, right? Most companies don't actually care if there are airplane crashes on their movies, right? It's only airplanes that get upset about this. So very different questions. So what size can I do? How much of the network do I fix? Is there some sort of unsupervised pre-training I could use to adjust it? Does that make sense? Where you're trying to figure out what I can use from the real world. Oh, augmentation. Can I augment the data with my plane crashes? Sure, I can shift them right, shift them left. Yeah. How do you get the negative samples? So how do I find 1,000 images that are not airplane crashes? Just sample random images off the web, pick random search queries. It's a good question, right? You want, in some sense, some large set. Ideally, you might actually go to the company who's your client. Now, you can't do this as a homework assignment. See what images they've been showing, right? So they've been showing a bunch of images and grab thousands of the images they've been showing. Most of those will not be airplane crashes. You can take those as a random sample. How else might you try to be cleverer about finding negative samples? Yeah.
So would you want something like similar to an airplane crash?
Wouldn't you like something similar to an airplane crash, but not one? Right, right. So it's really easy to tell something which is a bowl of soup from an airplane crash. Doesn't take a lot of training. In some trivial version, just the average RGB color distinguishes soup from airplane crashes. Make sense? So in some sense, what you'd like to do is to grab a bunch of training examples that are close and learn to distinguish those. That's the hard part. It's to distinguish the airplane crashes from the traffic jams in Los Angeles or whatever else looks like an airplane crash. So what process, actually, what's the machine learning jargon for a scheme that might find near misses? People who had 520 have seen this. What process might you use to find things that are almost airplane crashes or things you'd like labeled? Train your model on a few crashes and a few far from crashes, run it over a whole bunch of unlabeled data, and find the ones that it predicts to be high probability airplane crashes. Some will be airplane crashes, some won't. So you're going to label the ones that are at least somewhat likely to be airplane crashes. Not the ones that the computer's really sure are not airplane crashes, because it's people lounging by the pool and enjoying their cocktails. The jargon for this process? Not boosting, no. Good try. Not cross entropy. There's a whole field of machine learning where you try and figure out what images to label next. Active learning. Whole field of active learning that says that rather than taking a bunch of images and label them airplane crash or not, where almost all of them are not. 99.99% of images ever made are not airplane crashes. I just made that up, but it's true, I'm sure. You try and run your computer, predict things that are likely to be airplane crashes. Some will be, some won't be. Relabel those and repeat. So that's a way to find these ones that are maximally informative. Okay, so note what's happened. We've had to think about what architecture structure makes sense. We've had to think about what pre-training makes sense. We've had to think about how to get labels on these things. And other things we'll have to think about is loss functions. How bad do we feel about labeling something an airplane crash when it isn't? Well, false positives, false negatives, right? Which ones are bad for my problem? Maybe that's something we build directly in the loss function, and we do a gradient descent optimizing the loss function we care about, a different weight on true positives or false positives, rather than whatever loss function is symmetric. And often almost always, there's an asymmetry in the loss function, right? It's a different cost to let an airplane crash through rather than blocking something you shouldn't have blocked. And that requires, again, knowing your problem, your world. So I think for always to think, what structure is there? What do I know if I'm looking at SNPs in genes? What do I think about them? Do I have some idea they come close to each other? Am I concerned about the ones in the promoter regions? Do I care about introns? Do I care about exons? How might I decide which ones to look at? What window do I think they're going to be correlated over? Are there things I could unsupervised pre-train on lots of other genes that I might use to build a model to start with, right? So I think a lot of these things, the questions are, can I know something about my structure of my world? And most worlds, be they genes or languages, have lots of structure and lots of things that are similar. I want to do a language to do my nice stuff in Myanmar, and I want it not just in English, but other languages. How do I jumpstart from lots of data in English to something that's maybe less data? Right, so all these things, it's a question of what can I bring to bear about the world to define the pre-training, to define the architecture, to define the data augmentation, to define the loss function, to define the labeling of the data sets. Does that make sense? So Conrad and I are trying to push you as you do the projects to go beyond the Kaggle world where somebody else said, here's the data set. It's nice and clean. Just do it. In general, people who win competitions, especially in the real world, well, the first thing is, what other data can I use for the pre-training or pre-trained model? In the Kaggle world and the business world, what's the real loss function? What do I really care about as opposed to the thing that's built into PyTorch that's obvious? So to think always, what do I care about? What's the loss function? Which things matter? What is have to generalize? Here's another cool question, one I obsess with. We train the model on this data set for today. We're going to apply it on that data set tomorrow. The nice statisticians want to say, no problem. Just assume tomorrow is IID and looks just like today from the same distribution. True? Definitely not true. Tomorrow's different, right? Every time I open them, actually, it's been much the same today for a while, but open the paper, it's like, oh no, Ukraine still looks bad. But it is the case in general that the world changes, that the products that are introduced are different, and to start to think questions, okay, how would I apply this in a slightly different world? What's going to make it more stable? what things might change, right? Can you do some sort of minor domain transfer? If you've trained on airplane crashes, how will that help you do a faster job of detecting unwanted nudity in the slides being shown, the pictures being shown? How do you do some sort of generalization? Another question that makes it more interesting. I'm going to stop now, but if you have questions or feel you're stuck, be sure, email Edu, Slack, me, Conrad, Anka, anybody, your pod leaders, and we're happy to talk and propose things that are interesting and doable, which is the trick. Cool, cool. See you all online and next week.